Going back to the PPT. Right. So considering the three-dimensional box, we try to see that the possible energy levels for the particle in three-dimensional box is restricted by nx, ny, nz combinations. Nx, ny, nz combinations. Where nx, ny, nz take only positive integer values, and nx, ny, nz simultaneously satisfy a condition that nx square plus ny square plus nz square is equal to n square, another integer n. Okay. So with that, we try to find out what are the different possible energy levels. Okay, like with nx, ny, nz as 1, 1, 1, and nx, ny, nz. Okay, one of them being 2. You got 3. What do you say? Degeneracy states, and similarly, okay, we tried to understand that when we have a particle in three-dimensional box, it has discrete energy levels as well as it gives you degeneracy. Okay, particle in one-dimensional box gives you discrete energy levels, whereas particle in three-dimensional box gives you discrete energy levels as well as degeneracy. What is degeneracy? Okay, more than one particle having same energy, or to say we have more number of states with same energy. Okay, and then we try to see okay how many particles. Okay, when we want to calculate the number of intersections over here, you just have to find out the area and divide with the area of the square. So that will give you the total number of intersections. Similarly, the total number of intersections over here can be known if you know what is the area of this circle and divide with each of this. Divide the area of the circle with the area of each of this square. And when we try to find out the number of intersection between this two circles, then the number of intersections gives you, okay, number of intersection is given by, okay, finding the area and then dividing that area with the area of each square. Okay, that's what is same over here. Okay, now I just wanted to tell you that each square has got one intersection. Each square has got only one intersection. That's what I tried to explain yesterday. Okay, we have one intersection per square, or we have one square per intersection. So each intersection gives you one particular combination of nx and y. This is in two dimensions. Each intersection gives you one combination of nx and ny in two dimensions. Now, okay, I want to find out how many nx and ny combinations are there. How many nx and ny combinations are there for value ranging from for n value ranging from n to n plus dn. When I have n value ranging from n to n plus dn, I want to find out how many combinations of nx, ny, and z are there between these two. Okay, then that is clearly understood or easily understood by considering that n square is equal to nx square plus ny square plus nz square, but nx, ny, and z are all positive. That implies nx is positive, ny is positive, and nz is positive. That implies only 1/8 part. 1/8 part of the whole sphere, because n square is equal to nx square plus ny square plus nz square. Okay, okay, so this is the equation of a sphere, that is n square is equal to nx square plus ny square plus nz square is the equation of a sphere. But nx, ny, and z are positive. That implies I'll be considering only 1/8 part of that sphere. Okay, that is 1/8 part. Okay, now what is that I want? I want the total number of states between n and n plus dn. That implies I have to consider two spheres, one of n and then there is another sphere of n plus dn. Okay, so I have to consider the region between these two spheres. Okay, as I was considering, okay, the area between the two circles. Okay, similarly, in this case, in a three-dimensional figures, I have to consider the volume between the two spheres. Now, what is the volume between the two spheres? It is nothing but 4/3 pi n plus dn whole cube. That is the outer sphere, and 4/3 pi n cube is the inner sphere volume. So when I try to find the difference between these two spheres, that is pi 4/3 pi n plus dn whole cube minus n cube will be the volume between the two spheres. But out of those two, okay, spheres, I want only 1/8 part of those two. Why 1/8? Again, I want nx, ny, nz all positive. So 1/8 multiplied. So what we have is total number of combinations of nx, ny, nz. Okay, whose values range between n and n plus dn. Whose okay values range from between n and n plus dn is given by this expression, that is 1/8 4/3 pi n plus dn whole cube minus n cube. Okay. Then this 4 and 1/8, so it is 1/2. Okay, this is 1/3 and pi. Okay, and then this is expanded. This is what you get. Out of this expansion, I will neglect 3 n. Okay, okay, okay. Sorry. Okay, I'll neglect dn cube. Okay, I'll neglect dn cube and also neglect okay 3n dn square. Why? Okay, okay. Simple is I'm considering dn to be very small. Okay, sir, why don't you consider dn to be large? Okay, if at all if you are considering dn to be large, okay, that implies okay, uh, the whole expression is to be considered. Sir, why don't you consider the whole expression? Because most of the times when we consider giving energy to a system, the amount of energy given will be very small. Sir, where did the energy come into picture? Please remember, okay, K is equal to n pi by L, but it is also is equal to 2m by h cap square E under root, or to say K square is proportional to E square. So whether you talk about N or whether you talk about K or whether you talk about P or whether you talk about E, all of it all is almost all same except for multiplication of some factors. Okay, so when I talk about n, okay, you may say that I'm talking about E also. So if I'm giving some energy to the system, the amount of energy given to the system or taken away from the system will be very small in comparison to the total energy already existing with the system. So I generally consider dn to be very small. So when dn is very small, dn square will be much smaller, so neglected. Dn cube will be much smaller, so neglected. So I'm neglecting dn cube and dn square terms. So what I remain with is pi by 2 n square dn. Pi by 2 n square dn gives me the total number of energy states available between n and n plus dn. Remember, okay, we are looking for density of states, but what is that I said? Okay, this gives me the total number of energy states available. I'm talking about total number of energy states available. Did you talk about density? No, not yet. Okay, I did not talk about density yet. Okay, so this expression gives me, okay, pi by 2 n square dn, okay, gives me the total number of energy states that are available between n and n plus dn. Okay, right. Okay, that's what we did till yesterday. Now, in today's scale, okay, I'm giving you a match for, okay, match the following expressions here. Okay, let me hope, okay, you will go home and try to work it out. Okay, and try to solve these questions. Okay, this match the following. Okay, now if I mean, let me tell you clearly. Okay, please try. Okay, if you don't try, okay, what I can do is I'll be giving the answer and you will not be understanding why that particular answer. Okay, so please try to, okay, complete this match the following. Okay, so what is this? This pi by 2 n square dn gives you the total number of energy states available between n and n plus dn. Okay.